Hello, STT 315. This is recitation 14. So consider the following bivariate data. Our sample size n equals 40. Our x bar equals 90. Our y bar equals 190. Our standard deviation of x equals 2000. Our sample standard deviation of xy equals 4,500, and our sample standard deviation of y equals 12,500. And we want to find the regression line of y on x. So here we have our y equals a plus bx. So to find what our b is, we're going to do our sample standard deviation of xy divided by sample standard deviation of x. So that would be 4,500 divided by 2,000, which gives us 2.25. And then our a is going to be equal to y bar minus bx bar, because if you were to solve, if we had y bar equals a plus bx bar, if you solve for a, this is what you get. So it's just taking this and reworking it and having a equals an expression. And then that equals, so our y bar is 190. And then we're going to subtract our b times x bar. So we just found our b in the previous step, which is 2.25. And then we're going to multiply that by 90, which is our x bar. And that equals negative 12.5. So when you write out the regression line, it will look like this. Y equals negative 12.5 plus 2.25 times x. Consider the following regression of y on x. I believe that should be of. So here we have y equals 15 plus 0.5 x. And here we have our standard error of b, and this is our b and this is our a. So the regression was based on a sample size of n equal 200, and the number in the parentheses is the standard error of the regression coefficient. And so here we have, is there a linear relationship between the two variables? So here we have our, we would have, sorry, I'm blanking right now. Our z equal to, our z statistic equal to b divided by the standard error of b. So this is all given. So b is our 0.5 and our standard error of b is 0.25, which is 2. So now we can do our p-value, which is equivalent to 2 times the normal CDF of from negative infinity to 2. So the reason why we multiply it by 2 is because we want the area under the curve on the left and also on the right. And our 2 comes in, this 2 in our normal CDF function comes in from the previous step, because that's our z that we just found. So we have, so when you do that in your calculator, you'll get 0.0455, and at alpha equal 0.05, we're going to reject the null. And if there's no association, so the null is if there's no association. However, so we got a p-value of 0.455. So that is less than our alpha value, which is 0.5. So that implies that we'll reject our null, and then our, so there is a linear relationship. So consider the following bivariate data. Our sample size is n equal to 25. Our B1 is 5, and our standard or our sample deviation of, sorry, I've been saying standard deviation. I meant to be saying standard error. Sorry, previously in the other one. So this is standard error, and then actually that's correct what I said before. So sorry, I may have said standard deviation here. I can't remember. Anyways, that's standard error. Sorry. So going back here, let's start over. So number 3, consider the following bivariate data. Our sample size n equals 25. Our B1 is 5 and our standard error of B1 is 1. So the question is there a linear relationship between the two variables? Use a t-test with degrees of freedom n-2, and we're using a t-test because our sample size n is less than 30. Anyway, so our t is going to be equal to our B1 divided by the standard error of B1. So here we have B1 is 5 and our standard error is 1. So 5 divided by 1 is 5. And so if we were to draw out our t distribution, it's still a bell curve, and we have, since this is our t value here, so we have -5 and 5. So we want to find the p-value, the area under the curve. So I can find the area under the curve here, which is t CDF from -5. Sorry. So we're going to do 2 times t CDF. And so we would have t CDF of -5, 0 is our mean. And then our degree of freedom, which is 25 minus 2, because we're using n-2 degrees of freedom. So 25, our sample size, minus 2, which is 23. So our p-value is 0.00005. So that's very small. And so we're going to reject H naught, so we're going to reject H naught, which is no association. That's what our H naught is. However, I meant to write, since we're rejecting H naught, there is a linear relationship. Okay. Yeah, so there is a linear relationship because our H naught is that there's not a linear relationship. So if we reject that, then yes, there is a linear relationship between the two variables. Okay. So the regression analysis of a certain bivariate data resulted in SSE equal to 1,000 and our SSR equal to 8,000. And then what is the coefficient of determination for this regression? So it's asking us what is our R squared. So our formula for R squared is SSR divided by SSR plus SSE. So that equals 8,000, which is our SSR given, divided by 8,000 plus 1,000 here. And so when you calculate that, you'll get 0.888 repeating, which is 0.89 when you round it. What is the effect of linear transformation on the coefficient of correlation between two variables? So the answer is no change. Our R squared remains the same after linear transformation. Number 6. The mean height of American women is about 63 inches, and the standard deviation is about 2 inches. The mean height of American men is about 67 inches, with a standard deviation of 4 inches. The correlation between the heights of husbands and wives is about 0.5. We want to predict the height of the husband whose wife is 62 inches tall. The slope of the appropriate regression line is, so it's asking our B is our slope. So to find our B, we're going to take our correlation times our standard deviation for y divided by the standard deviation for x. So here we're going to have our x be women and our y is men. So our correlation was given to us as 0.5. Our standard deviation for men is 0.4 given here. And then our standard deviation for women is 2. So this, our b equals 1. That's our slope of the regression line. So now if we want to find the intercept, which is a, of the appropriate regression line, so our a equals y bar minus bx bar. So we already found that our b is 1. So we're going to have our average height for men subtracted by 1 times the average height for women, which is 63. So 67 minus 63 is 4. So that is our intercept, is 4. Now we want the predicted value of a husband's height when a wife's height is 63 inches. So here we have our same equation, linear regression of y equals a plus bx. But we already found our a from before and we already found our b. But now we want to have, so we found our a in number 7. And we found our b, which is 1, in number 6. And our x is given right here. Our wife's height is 63. So now we want to find, okay, what is our y? Because we want the predicted value of the husband's height, and y is men. So at x equals 63, our y equals 4 plus 1 times 63, and that equals 67. And I hope this was helpful. This concludes recitation, and I know it was a shorter recitation. So yeah, I hope this was helpful, and this concludes recitation 14. Bye.